Okay, do you see it in full screen?
Yes.
Because I'm a presenter. Okay, great.
Looks good.
Okay. So my name is Ivan. Wait a second. Okay, here I go. So my name is Ivan Radchenko, and I'm a data professional. Wait a second. It's it started a slideshow for some reason.
Yeah, no, take your time. I think you can stop that slideshow.
Okay, so start from the beginning. So my name is Ivan, and I'm a data professional and with more than 10 years of experience. And currently, I work at Madeira Data Solutions. It's a consulting firm primarily. We have a lot of clients all over the world, and I have a lot of experience in BI, and also before that I was a development DBA, and my previous workplaces allowed me to gain a lot of experience in innovating and implementing all kinds of creative solutions, and one of them is Columnstore indexes. And when you're talking about Columnstore indexes and where you're approaching and considering it even, there are two main questions, why and how. So this presentation will mostly focus on why, because I find that in my personal experience, the most challenge I had when implementing Columnstore indexes was to actually convince a client or a manager that it's a good idea. So first of all, what we need to understand when we approach this challenge is how do we evaluate our database and understand which tables are a good fit or a perfect fit, and which tables are a poor fit for a Columnstore index. So that's what this session will help you understand. So it assumes that you have some familiarity with your own environment, and excuse me, Dipankar, did you take control just now? Because something's changed.
No, I didn't take any control. Let me see if.
Okay, let me take it back. I took it back. I took it back. It's okay. So where was I? Right. So you need to be familiar with your own environment and your workload to better understand if it's a good fit for you, if Columnstore indexes are a good fit. So so let's start with the basic architecture. First of all, if you're familiar with the regular tables in SQL Server, the way they're stored is SQL Server uses pages, 8 kilobyte pages, to store rows. And depending on the row size, a number of rows can fit into a single page. And that's how any table is built, whether it's a clustered index, whether it's a non-clustered index that sits on top of the table. It's structured like that. But on the contrary, the Columnstore index, it stores columns. It means that when you're querying a table that is Columnstore and you're selecting A, B, and C columns from the list, it only retrieves the data for those columns and not the whole row. And that's basically the main feature. So when you see this, when you're looking at this architecture, so what you see here is, first of all, those are the rows that we're going to load. Let me. Do you see my cursor?
Yes.
Yes.
I
Okay.
see them. Yeah.
So first of all, we have a row set that we want to load into the table, and it starts from there always. So the way Columnstore index works, that first of all the rows enter into what's called delta store, and it creates row groups that can contain up to basically 1 million rows. And once this row group is formed, then there is a background process that compresses these rows, each column at a time, into segments. And this is how Columnstore architecture is being, formed. So because it every segment of the index contains the data of only one column, it enables a compression that is unprecedented, and it's unachievable for the regular row store table that has all sorts of data types. So that's why when you're dealing with only one type of data, be it an integer or a varchar, it's a lot easier to compress it effectively. And that's why Columnstore indexes have the best compression that you can achieve in SQL Server. And so the way it works, like you see here, first of all, the data is stored in segments up to 1 million rows each segment. And first of all, the row groups are created, and then they're compressed and inserted into the index, and it all happens automatically into the background. And when you insert something into the table, the transaction is considered committed once all the rows are written into the delta store. So all the compression happens in the background. So technically, we have a question: is it a new feature in SQL Server? So no, it's not a new feature. It existed since SQL Server 2012, but initially, or 2014, I think. Yeah, but initially it wasn't updatable. So the way it worked was every time you needed to insert new rows into the table, you needed to drop the column store index, insert the rows, and create the index from scratch. So that was very cumbersome and not very useful. That's why it only became, sort of useful in SQL Server 2016. So, okay, let's continue. First of all, column store index is not technically an index because you can't seek it. You can't find the row. Okay, so the way regular indexes, clustered or non-clustered, work is they help you retrieve, first of all, find and retrieve a row or a set of rows without scanning the whole index or a table. But wait a second. I lost control again. Let me.
Yeah, you're there.
Let me return back to my. Someone keeps taking the control. I don't know. I just have to take it back all the time. So I have a notification that another user took control, and I don't know exactly who. Okay, so regular indexes, they come in clustered and non-clustered varieties. So the clustered index is basically the structure of a table itself. Whenever you insert the data into the table, then it's automatically being ordered by the index key. And so the rows are inserted in the proper places, in this order. And non-clustered indexes, they sort of sit on top of your data, and they point to the clustered index using the clustered index key, which is stored in every non-clustered index that you have. So that way, when you're using the non-clustered index, sometimes you don't have to access the base table, and sometimes you do. It depends on the query. But Columnstore is very similar. You can create a clustered column store, which is the base table itself. You convert it into a column store structure. The difference is it doesn't really support sorting right now, although in the next version of SQL Server in 2022, they're finally addressing that, and it will have sorting options. But right now, sorting is very important when you insert the data into your table, but the index itself, it isn't aware of it. That's why I'll touch it in more detail in the later on. So you can choose to create a clustered index, a clustered column store index, which means that you will convert your table to the clustered column store index. And then you can have additional non-clustered indexes on top of it, if you wish. The basic idea is that the column store indexes are more useful for analytical queries, and the regular indexes are more useful for OLTP queries that retrieve a small number of rows. Like, for example, when you select a person details or a customer details by customer ID or his or their passport number, you retrieve one row or a small number of rows. So in this case, regular indexes are very useful because they are very efficient at retrieving a small number of rows, while column store indexes, they are more efficient when you aggregate your data at large scales. So that's why you can create a non-clustered column store index on your regular table so that it sort of answers any any problem that you throw at it. It can support very small OLTP queries, and it can also support analytical queries. But being a jack of all trades, it's really a master of none. So that's why it's not usually very worthwhile creating a non-clustered column store index on top of your table. That's all based on my experience. Although I do have clients that use that. They use that feature and they use that pretty successfully. So a good example why you would need an additional non-clustered index on top of clustered column store index is when you want a primary key, when you want to enforce uniqueness, for example. So you can create a non-clustered primary key on top of your clustered column store. Okay. So feel free to stop me if you have any questions. If you know, I need to explain something in greater detail, something. So like I said earlier, in the beginning, the earlier versions of SQL Server, clustered column store indexes weren't updatable. And this diagram explains basically why. They pretty much are not updatable even right now. And their updatability is sort of fiction, is like a workaround that Microsoft implemented to give you an illusion that it's updatable. But what happens, what really happens is whenever you delete rows from the table, from your clustered or non-clustered column store, what happens is it creates a bitmap, and it and it stores the rows that were deleted or pointers, so that the engine knows that those rows, they are not relevant, they are obsolete, so it won't retrieve them whenever you query the table. So the rows aren't actually deleted. The rows actually remain in the basic structure, but they are excluded from the result sets. And that is why whenever you delete anything from the column store index, you cause fragmentation. You cause like rows that are no longer valid. And to fix that, really, you can either reorganize or rebuild it, just like a regular index that you're used to. But still, it's a pretty resource-intensive operation, and I also mentioned the sorting before that, and although you can pre-sort the data when you load the data, but whenever you delete rows and then rebuild or reorganize the index, SQL Server disregards this entirely, all the sorting work that you did, and that basically breaks the sorting. So that's why in order to I lost my train of thought. Make sure that the order is kept, is conserved. It's very important not to delete a lot of rows or update a lot of rows in your index. So still, it shouldn't stop you from implementing column store indexes if your table has updates. Okay, so that's exactly what this presentation is for, is to consider all the pros and cons, but ultimately they still can be very worthwhile for you even if you have a lot of cons. So you can modify the data in the column store index in 3 ways. Either, right, you can delete the modified rows and then reinsert them, or you can update and insert, or you can merge. You can use a merge statement. So apparently, and I learned it a hard way, there is a huge difference between these 3 operators. Basically, the logical operation is the same. Whenever, because the index itself is not updatable, whenever you modify the rows, it deletes or it marks the deleted rows as deleted, and it inserts new ones into the data store in each of these three cases. But they are not equal in performance. And since you know the best way to update the column store index is to insert the rows. So that's why delete and insert is by far the best way. And the upsert is worse, and the merge is absolute worst. It's just a nightmare. It's especially if you load a large number of rows, then the differences are non-linear and they're huge. Delete and insert can take you, up to a minute, and merge will take you 20 minutes. And I'm not exaggerating. So just remember that it's the main point of this. You always want to delete all the modified rows and then insert them from scratch, unless you have no choice. Then you can use the upsert or as a next best thing, and merge as a last resort. So maxdop is the additional thing that you should consider, especially on the older versions of SQL Server. Whenever you insert the data into the Columnstore table, if the SQL Server, the engine, chooses to insert it in parallel in I don't know, 4 threads, it means that it will create 4 row groups, and it will load those row groups in parallel. So let's say you have 1 million rows to load, and you're loading them in parallel in 4 threads. So what happens is you will have 4 row groups that are each more or less 250k rows. So when they are compressed and inserted into the Columnstore index, you will have 4 smaller segments. But if you insert the same data with maxdop1, okay, in a single thread, then you will get a single row group that will be compressed in a single segment. So that will be more efficient, and it will enable better compression, because the more rows there is in the segment, the better the compression will be. So that's why in some cases on the earlier versions of SQL Server, I noticed when I examined the execution plan that it would insert the data in parallel. So I would force it with maxdop1. But on the newer versions, I noticed that it doesn't do that anymore. It knows that it's not efficient to load the column store in multiple threads. So what it does, it parallelizes the plan up to this point. For example, if you select the data from another table and insert into the column store, then it can do everything in parallel except for the insert itself, and that's an ideal scenario. That's what you want. Okay. Oh, and by the way, if you add order by in your insert, and you order by the column that you want to make the column store ordered, it will also force insert in one thread, because before it can insert the data, it will have to sort it, and everything up until the point of insert, it will be performed in parallel, and then it will insert the sorted data into the data store. Okay, any questions?
Ivan, there is a question from Arthur.
Yeah.
If we can or should defragment the Columnstore indexes.
I can't hear you very well.
The question is, can you defragment Columnstore indexes?
Yes, we can reorganize or rebuild the index, and it should be done in my experience, every time that you insert the data, but only if you delete it, if you updated the existing rows. So this question is slightly out of scope for this lecture, because when we get to the last slide, I'll explain the process that I wrote, and it contains the index reorganize part as well. Okay, so we had another question. I couldn't read it. Dipankar, can you read it, please?
The other question. Oh yeah, is it good for a line of business OLTP database or just for data warehouse or BI?
Okay, yes, it's mainly for the analytical data warehouse or BI databases, because like I said, when you're working with OLTP, you mainly want to select a very small number of rows. You mainly use where clauses that filter by an ID number or a passport number or something like that. You don't want to aggregate a lot of data. So that's what regular indexes are very efficient for. And on the other hand, Columnstore indexes, they contain segments, and every segment contains 1 million of rows maximum, and it's a unit. So when you select data from the Columnstore index, the basic unit is a segment, so you can't retrieve a single row. You first retrieve a segment, you scan the segment, and then you retrieve the row that you want. So it's not efficient at all when you want to retrieve a few rows. Okay, so I hope this answers it. Okay, so how do you determine potential candidates for your Columnstore table? First of all, table size and row count. Basically, the larger the table is, it's more likely that it will be a good fit for a Columnstore index. The most obvious advantage is the storage space. Columnstore indexes offer just crazy levels of fragmentation of compression. So that's why I have a lot of clients that use Columnstore indexes for the archive tables that they don't query very often, and the only reason basically they wanted to convert them into the Columnstore is to save crazy amounts of storage. So that's the first criteria. Okay, the second criteria is the workload. So the workload means that the queries that are basically running on your system the most. So first is the aggregate queries, and second is queries that retrieve a small amount of columns every time. Like let's consider this scenario. You have a table that has 20 columns, right? A regular table, not Columnstore. And sometimes you search by column A, where column A is between such and such, and sometimes it's column C between such and such, and sometimes it's column D. In this case, you will need 3 non-clustered indexes on those columns at the very least to enable efficient querying of this table. But if you have a Columnstore table, on the other hand, and you select only a small number of columns every time, then you don't need to create specific indexes for every query or every set of queries. When you retrieve a small number of columns, 3 or 4 columns out of 20, let's say, then it will be a huge benefit to scan only those columns and not the whole rows. So that's why that's what you need to pay attention to when you're browsing your workload and learning about it, and considering if Columnstore will be a good fit for you. So 3 is the load pattern. So load pattern means how much data are you updating and inserting. So the insert update ratio, and the higher it is, the more inserts you have, the better for the Columnstore, because like we discussed in previous slides, updates is a pretty painful operation for it. So the more inserts you have, the better. And also row count is very important, because since it works best when you're inserting in large chunks, so that it can compress the segments into 1 million rows per segment. That means that basically, if you have less than 1 million rows, that's not ideal. So it shouldn't stop you. It is a detriment, right? But it's not a showstopper. So you have a lot of solutions for that. For example, if you're inserting, for example, a couple of 100,000 rows per day, you're not coming close to a million. You can first of all, it's not the end of the world. You will get smaller segments, but it might be worthwhile anyway. You won't have segments that will be 1 million rows, but in my experience, it will can still serve you very well. And also, you can use buffer tables. Like you can, instead of inserting all your data into your Columnstore table, all the time, you first insert the data into some buffer table, and when the buffer table gets more than 1 million rows, for example, you can insert the rows from there. And it's a slightly more complex solution, but I have implemented it once for one client, and it works great. It just requires you to use a view that behind the scenes it unions between both tables. So when people query the table, they don't really know that you're querying 2 tables and not one. So that might be cumbersome. Okay, so fourth is the limitations. So Columnstore indexes have quite a lot of limitations. Standard edition, yes, I think so. I think the standard from SQL Server 2016 or 2017. I'm not sure about that. I knew that before, but I forgot. I'm sorry. But yeah, I think lately in the latest versions of SQL Server, they are not Enterprise Edition anymore. First of all, large objects like varchar max or varchar max or binary max are not supported. And that applies to 2017 and below. And primary keys and foreign keys are unsupported as well. The reason for that is since you can't seek like a Columnstore index. Like I mentioned earlier, it's not really an index. So implementing a primary key would be very inefficient from performance perspective, and foreign keys as well. So you can work around that by creating a unique non-clustered index that will basically serve as a primary key. So the only difference between a unique non-clustered index and the primary key is that in the non-clustered index, you can have one null value in your key column, and in primary key you can't. But that's a minor difference. Basically, if you create a unique non-clustered index, it should be enough for ensuring that your data is unique. So you don't really need the primary key. So how do you go about evaluating pros and cons? And thus you come to a conclusion if it's worthwhile to migrate a certain table. So first of all, it's like I mentioned earlier, how many columns do you query and how often? If you query a few columns at a time, then it probably means that you have a lot of non-clustered indexes on your tables right now. You have a clustered index that's ordered in a certain way, and then you have a lot of non-clustered indexes that serve the queries. So if that's the case, then it's a strong possibility that the Columnstore will be a good fit for you, because you will no longer need all those non-clustered indexes, and the clustered Columnstore will solve your problem. And the cons, on the contrary, if most of your queries retrieve a lot of columns. So when this happens, what it means that if you have a table that have 20 columns and you very frequently retrieve 15 of them, it means that you don't really have much benefit or detriment when you're retrieving the whole row, because you're using most of the columns anyway. So retrieving the whole row is not really that bad. So the only benefit that you have from Columnstore is the compression. It can still be beneficial, like we will see with the other entries, with the other pros and cons. But basically, when you retrieve all the columns, or basically all the columns, so the only real difference that Columnstore makes is the data compression. So effort is not really relevant for this specific entry. So let's continue. So the next issue that you should consider is the insert sizes, the bulk inserts. So like we said, more than 1 million rows is very good. If you're inserting more than 1 million rows at once, it's a very good sign that Columnstore will be a good fit for you. The opposite is true as well. So if there are smaller insert bulks or a large update insert ratio, if you're mainly updating the data and not inserting new rows, then it probably won't be a good fit, or at least it will be more challenging to implement. So the effort required, like I said, the more updates, the more effort will be required, and the less efficient will be. Someone said in the chat, clarified about the additions.
That's right. From 2022, all additions are supported. The catch is in the amount of cache it allocates, which is quite low in the standard edition.
Yep. Sounds about right. Okay. So the next is the amount of sources for your table. Whenever there are a lot of sources, let's consider for a minute a regular table that I have right now, right? Not a Columnstore table. And there are a lot of stored procedures or maybe regular inserts that update the data in this table. So it can have blocking and all that. So SQL Server is pretty good managing multiple sources and inserting data in parallel. But in the case of Columnstore, because it works great with large chunks and not very good with small chunks, or not good at all, I should say. That's why when there are a lot of different sources with smaller chunks each, or even single row, then it's not a good fit at all. But still it can be worked with. It's not a deal breaker in and of itself, but sometimes if you have, for example, 3 or 4 sources for your table, for example, Google Analytics or something, or maybe some data lake, or and some other source, and you aggregate data from each of those, then maybe you will insert all the data into the staging table first, and then when you consolidate all the sources like that, then you will insert all the data at once into your Columnstore data table, something like that. So the more sources means more effort required to optimize the load process. Okay, both performance and blocking implications. So that's what you should consider. And the last one is the workload. When you have analytical workload that scans huge ranges of data, for example, for last year or last 2 years or last few months, and it aggregates that into a report, that's what you want for optimal Columnstore workload, for a workload that fits the Columnstore index. And on the contrary, if you have your typical workload 6 and retrieves a small number of rows, then it won't be a good fit. It's not good at that. So the more OLTP queries, the more non-clustered indexes might be required on top of the Columnstore index. Or on the contrary, you can create a non-clustered Columnstore index on top of your existing table, so that you can handle both OLTP and analytical workload. Although it's, like I mentioned previously, it will be a jack of all trades and master of none. So that's why in most cases, it's not a good solution. The best solution would be to split it up and keep your OLTP database as OLTP only, and then load the data into a separate database that will have Columnstore tables, and use that for your analytical queries. So that would be the best option.
Ivan, I got a question.
Yeah.
So, I mean, you mentioned large bulk insert more than 1 million node. That's good. But for example, after you insert, when you're gonna, select those data or query those data, is that also faster with the
Is that what?
Columnstore? Is that also faster with the Columnstore index?
What is faster?
Like querying the data, making the query and selecting the data from the table.
Yeah, sure. But like I said, it's just okay. Let's say you have a query that selects 3 tables, aggregates them. Like, for example, you have a hospital and you have patients that have lab results, and you want to return the query that gives you a list of patients and how many, for example, lab tests they had. In the past month, so you're selecting the patient name and you sum all the results, all the tests, and the where clause you put where date between now and 2 months back, right? Something like that. So what happens is the SQL server retrieves only the 3 columns or the 2 columns that you requested. And since they're compressed very well, it means that the IO that it will have to do will be a lot less than if you were even seeking the regular index. That's why you will be saving IO. And that will indeed make the query a lot faster.
Got it. Thank you.
Okay, welcome. So to summarize this pros and cons table, basically, if your potential candidate table fits all those criteria, then it's a great fit. It should be a no-brainer for you. Unfortunately, it's rarely the case. So if you have the table that fits this more, then it means that it probably will not be a good candidate for a Columnstore index. And most of the tables lie somewhere in between. And that's what you should, where you should consider if it's worth it. And I'll just give you an example, which was a most challenging one that I've ever encountered. And still, it required a lot of effort to implement, but it was well worth it in the end. And the table in question had 500 columns, and it wasn't very big, like 10 million rows, which is not a lot for a data warehouse. And it was it contained players. It was an online casino. I used to work in an online casino, and this table, it was a dim table. It was a dimension, not a fact, and it had players. Okay, all the player information, and so the update ratio. Okay, so first of all, yeah, I'll it did. Oops. So it did fit this criteria. It had a lot of columns, most of which were seldomly queried. So we had a lot of non-clustered indexes on this table. And that was my primary motivation why I wanted to convert it to clustered Columnstore, because it was so unwieldy. It was insane. So despite that, newer players are pretty hard to come by, and most of the changes in this table were updates, I still was determined to convert it into Columnstore, and this was the major reason why. So, and also the bulks, the updates, the inserts, it was a couple of hundred, maybe every night. So couple 100,000 rows every night. So it was small. It wasn't large at all. So it definitely fit into this criteria. But still, because the original table contained so many non-clustered indexes, I think like 30, it was an insanely heavy operation to update this table. So the fact that I got rid of all those indexes and I had only one clustered column store and the primary key on top of it, that enabled me to achieve better performance of the updates than when it was a classic row store table. So this table also had a lot of sources. There was a huge amount. So we had a very big challenge to implement parallel updates of the table, and it was a nightmare. frankly. But that's the reason why I give you this example, because even sometimes the tables can be a nightmare to convert to Columnstore. It can be well worth the effort, and in this case, it definitely fit this criteria. Then it was analytical workload, and since it was a main dimension in this data warehouse, it was basically a main table in any report ever created that ran in this data warehouse. So overall, the impact was insane. It was a light and day difference. So that's why that's basically the purpose of this lecture, to give you the tools to evaluate pros and cons in such a way so you can understand and expect the right benefits, and that's how you can convince your manager or your client to go ahead with it. So do you have a question? Yeah.
There is a question, yeah.
Joins yes. Okay. So when you join, like let's say we have mainly fact tables, right? Fact tables, most of the time they're queried by date or by date range or something like that. So whenever you query those tables, you don't have any choice except to retrieve this whole date range. So yeah, you can't join as efficiently as you would using a regular index or a primary key, but it does a hash match, and it works. So overall, the benefit of retrieving a lot less data, and that's why these queries also consume a lot less RAM, and overall, this benefit far outweighs the hash match join that they have to perform using Columnstore indexes. And like I said, primary key, yeah, it's not really supported, but unique non-cluster indexes are supported. So sometimes you can utilize those if you want. Okay, did I answer a question, Alex?
Yeah, Alex, if you want to also speak up, you can talk and ask. We would love to have the, like both of your conversation. If you, just feel free to if you need to have more details.
So we have another question. A new functionality in SQL Server 2022. Yes. So the main new feature that I'm aware of is the sorting option. So you will be able to specify the sort order like a regular cluster index, and the best part is that when you rebuild or reorganize it, it will take the sorting into account, so it won't screw up your perfect, pre-sorting that you took care of when you inserted the data to begin with. So that is the main feature that I'm very excited about. But still, it's not really a deal breaker anyway. So, like I said, I had a lot of tables that had huge absurd ratios. So I had to reorganize the index every time I inserted new rows. So the sort was all messed up, and still it performed far better than the table ever, the roster table ever could. So that's why it shouldn't be a deal breaker at all. So implementation, since we mostly concentrated on why, here's a little slide on how. So first of all, you can create a Columnstore index in the following ways. The most straightforward way is to drop the existing clustered index and create a clustered column store instead. But no, it's not really an option in most cases, since those tables tend to be very large. So that's why usually we do it by creating a new table side by side, and then loading this table in chunks, and then switching between them. And since we have a bit of time, I'll tell you about column statistics as well. So column statistics, those are very important in Columnstore indexes, because when you select the data from the index, the data is stored in 1 million, approximately 1 million column, 1 million row segments. So it's very important for SQL Server to know the distribution of the data in the segments, so it can do what's called segment elimination. It's like it knows which segments it doesn't need, and it doesn't scan them. And it only accesses those segments that it thinks are necessary. So the column statistics are very useful for that, and that's why in regular tables, usually the auto-created statistics are created on the join tables, or on the join columns. Usually, if you use columns in queries to join on them, then statistic on this column will be auto-created. And in Columnstore, you need basically all your columns should have statistics on them. That's why in my solution that I wrote, that is a set of migration scripts, it contains a step that creates all the statistics, beforehand, so that they don't have to be created on the fly when you start using the table. Also, I'd like to mention partitioning for a minute. So partitioning can be a huge benefit when working with Columnstore indexes as well. Because like I said, SQL Server is pretty good in doing segment elimination, retrieving the necessary segments and disregarding the segments it doesn't need in this query. But partitioning can help it immensely. If you, for example, query mainly by date, and your table is partitioned by date, that's how SQL Server can limit the scan to the specific partition, and it will be a no-brainer for it to not access some partitions at all. So that's why partitioning can be especially beneficial for Columnstore index performance, and not so much in regular tables performance. Mostly partitioning is used for maintenance purposes in regular tables, and are not very good at improving performance, at least out of the box. But with Columnstore, they can be. Yes, so a few more questions. Does the query optimizer work for column stores effectively as conventionally? Yeah, so that depends on the SQL Server version, but I've been working with it since 2014, and it had huge problems that don't exist now. For example, the first problem I already mentioned before it used to insert data in multiple threads, which is not a good idea. So I used to put max.1 in every insert, and it was not always very good, because I basically forfeited the SQL Server parallel execution ability, but it was what it was. And the second issue, which was also very prevalent in SQL Server 2014, is when you have a a clustered column store index, and on top you have a non-clustered primary key, then it used to prefer to seek by the primary key and then do key lookups to the column store index. It was such a nightmare. You can't even imagine. It's like I said, the column store index, you can't really look, you can't really search or perform a seek on it. So every time the SQL Server retrieved the row from the non-clustered index, it was trying to look it up in a clustered index, and it would retrieve a segment of 1 million rows per every row from the non-clustered index. It was just not a good idea at all. And in my experience, it doesn't happen anymore. I haven't encountered it in the newer versions of SQL Server, but still, it's a very good point that you're bringing here. That's why it's not a good idea to combine a column store table with a lot of non-clustered indexes, because you never know when SQL Server will suddenly decide to do a crazy thing like this, to use some non-clustered index with key lookups to the column store. It might happen even in the newer versions. Okay, so is it a good idea to keep both types of tables in the same database? Yeah, sure. There's no problem at all. No, really. Nothing I can think of. No problem at all. I can mention storage distribution or partitioning, that you can maybe create a different file group in the same database for your column store index to leverage maybe your storage more efficiently. So for example, if you know that you are retrieving huge rows or ranges of data, then maybe if you create a partition function and partition scheme, or even file group without partition, just a file group that leverages your storage in such a way that you end up querying multiple disks, then it might give you a good benefit in performance. So you can use the same database, but maybe using a different file group will be a good idea. Is there any naming convention? So I don't think so. I mean, users, I don't think they should care. I think that from their point of view, it's a table like any other. If you have power users that are good with querying and know how execution plans work, then maybe it will be beneficial for them to know which type of table they are querying. But most of the analysts that I'm familiar with, that I encountered, they are not really familiar with execution plans all that much. That's why I was just trying to make life easier for them and make it as transparent as possible for them, and not bother them with different types of tables or anything like that. And so, bye, Thomas. Thank you. Okay, so that's it. I'm thinking maybe I will do a follow-up session on this that will concentrate on the how do you implement your Columnstore table once you decided to go ahead with it. And right now you have this set of scripts in our GitHub, and you have documentation there. The documentation is very detailed, and the scripts, I think, are pretty straightforward to use. They are parameterized, so all you need to do is just enter, supply a few parameters, and they will generate the whole process, like creating a new table and inserting the data into a new table, then creating statistics on the table. They will generate all the scripts for you. So you will have to test them, of course, but I think it's pretty straightforward. And of course, if you have any questions, you can email me. And unfortunately, I think I forgot to put my email here. So
that's fine. Ivan, I think I will get it from you, and because we're going to share this content with all the audience, and I will share that your information too. Yeah.
Sure, of course. And if you can put this link in the description on the recording on the YouTube channel, it will be great as well.
Oh yeah.
The link to the GitHub.
Oh sure.
Great. Yeah, and the documentation file in the GitHub contains my email. So if you read the documentation, you'll be fine. You'll find my email there.
No, that's great. No. Anyone have any other question to Ivan? But please feel free to ask it, or unmute yourself, ask the question. If not, Ivan is not going anywhere. He's one of the expert in Toronto. Always you can reach to him, and I will find out if we can have another session from Ivan for the following. Yep. If you don't have any question, then Ivan, thank you so much for your time. It was really great session, great learning, and thank you so much for joining. Everyone, happy holiday and enjoy the nice weather outside. It's like white, right?
Yeah. Happy holidays.
Okay, folks. Thank you so much.
Okay. Thank you very much.
Take care. Stay safe.
Thank you. Bye, everyone.
Thank you so much.
Deepankar, I'll stay a little. You want me to stay, right?
No, it's okay. I think you can leave it. I'll just also close the session.
Okay, if you need me, just ping me.
No, sure. Thank you so much, Evan. Thank you.
Great. Thank you.
Have a great one. Thank you.
Bye.